In this video, we are going to analyze amplification of signals from transducers. Okay. The main reason to do that is this. Doing this analysis will really help us understand how to apply the two rules of isolated amplifiers. Okay. The way we are going to do that is by looking at three particular example problems. Let's start by looking at the two rules of the amplifier that's isolated. The first rule is that the voltage at the two input terminals, say V plus here and V minus here, those two voltages should always be equal. The amplifier will force them to be equal. First rule. Second rule, there can't be any current that enter the input terminal. So if there were an I plus here, that should be equal to 0. Similarly, if there is any current into this terminal I minus, that should be 0. That's the second rule of ideal isolated amplifiers. Those two rules, let's go analyze three specific transducer circuits. Let's start with a very simple example of a photodiode. Okay, so we have a photodiode that's connected to a op amp like this in a inverting configuration. What we know is that the responsivity of the photodiode is 0.9 amperes per watt. That is, if I were to shine 1 watt of light into this diode, it's going to generate 0.9 amperes of current. Okay, that's the characteristics of this diode. On that diode, we shine a light of 1 millivolts. We get an output voltage of minus 1 volts. Okay. The question is, what is the resistance that would result in such an output voltage minus 1? This is a really simple problem. Okay. All we need to do is to directly apply the two rules of op amps. Op amp is already isolated, so just apply the two rules. This terminal, positive terminal, is grounded. It means the negative input terminal is also grounded. Virtually it's grounded. So this potential is 0, which means this potential is also 0. Okay, apply the first rule. Second rule, whatever current that flows through the diode or because of the diode, all of that current should enter this branch. None of it should enter the input terminal here. That's the second rule. Okay. Using those two rules, now we can relate the current, resistance and the voltage. That's straightforward. The current is 0 minus V naught by the resistance R. Okay. So first of all, this term here is V naught is minus 1, so this term will become plus 1. Okay. So this term is 1. Substitute for V naught, that is known. Okay, so from here we get R is 1 over I. How do you find I? That is straightforward. What this diode does is already given. 1 watt would result in 0.9 amps, right? So what would 1 millivolts result in? Result in 0.9 milliamps. Okay. So you plug that in here for the value of current. So this should be 0.9 milliamps. So this becomes kilovolts. Okay. And if you calculate 1 over 0.9, I think it is 1.1. Okay. A very simple problem involving a photodiode and an inverting amplifier. All we needed to do was to write the two rules of an isolated amplifier. In this example, we are going to look at a resistance temperature device connected to an op amp in this configuration. Okay, so a DC voltage of 1 volts is applied to the positive terminal, and the negative terminal has a feedback with the resistance RT and a grounded resistance. This is 100 ohms. Okay, and the characteristics of this particular device RTD is given. That is, the resistance in it linearly depends on the temperature. The constants here are not an alpha are given. What we want to find for this example is the output voltage that's measured across this RTD. Okay, it's not measured from the ground, it's measured across the RTD when the temperature is 100 degrees Celsius. Okay, is the question clear? We are given an RTD circuit, op-amp circuit. The RTD characteristics are given. We want the output across it at a particular temperature. Okay, so this is pretty straightforward. Let's first try what RT is at T equal to 100 degrees Celsius. Just plug in the values here for R naught alpha on T. So alpha is already in degrees Celsius. So just plug in degrees Celsius. We have 100 times 1 plus alpha times T should be 0.39. Okay. So 1.39 times 100, this should be 139 ohms. Now we know what the resistance value here is. We need to find what the voltage across it is. It's pretty straightforward. If there is a DC voltage of +1 here, the voltage here should be +1. Why is that? The voltage here and the voltage here should be the same, which is the voltage here. So this should be 1 volt at this node. Okay. So given that, let's go find out what V0 is. How do we do that? Let's use the other rule of amp, which is, let's say a current I flows here. None of that can enter this arm. All of that should enter this particular branch. Okay. So let's relate the currents there. I here should be V0 by the resistance RT. If you notice, it's not V0 minus 1 because the resistance across this RT device, that the total difference is V0. So it's V0 over RT. That current should also be equal to current in this branch, which is 1 minus 0 by 100. So we know what RT as 100 is, it is 139. So this is 139. Okay. So using this, we can find what V0 is. V0 is 139 over 100, so it's 1.39 volts. A very simple problem. Okay. And you can get the solution using these two rules within a matter of 30 or 40 seconds. In this example, we'll look at a temperature sensor. Okay. So we have a temperature sensor where the current through it depends on the temperature. Specifically, the temperature is 1 Kelvin, it will generate a current of 1 microamps. Okay. So we have such a temperature sensor, and that's connected in a op-amp circuit like this. Okay. For the particular example that we are considering, we know what the output voltage is. Let's say it's 2.1 volts. The question is, given this circuit, given this particular output voltage 2.1, find the temperature that would have caused this. Okay. So this problem is slightly tricky because there is one intermediate variable. Let's see. If we know what this current is, okay, we can find what the temperature is. Because 1 microamps is 1 Kelvin, with 100 microamps it will be like 100 Kelvin, right? So if you know what I is, we can find what temperature is. Question is, how do you find I? What we are given is this variable V0 output voltage over there. Okay. So let's try to find out I. Okay, let's see what I is in this circuit. There is a current flowing here. We know none of it will enter this circuit. So all of it should enter this circuit. Okay. So at this point you realize we know this resistor, and if we somehow know what this voltage is, we can find out this I, right? So there is this intermediate variable V dash. If we figure that out, we know we can find out what I is, in turn we know what temperature is. And of course, relating voltages in an op-amp circuit is usually easy. So we know, let's call this intermediate voltage V dash. This is V dash here in this negative terminal. It is V dash here in this positive terminal. Okay. So at this node, we have V dash. This is the first rule of an isolated op-amp. The two input voltages will be the same. Now relating V dash and V naught should be straightforward. How do we do that? It's called the voltage divider rule that applies in this case because say there is a current I dash flowing in this branch, okay, that should be the current that flows in this branch because none of it could enter the positive terminal. And whenever that is the case, voltage here gets divided or split based on the ratio of these two resistors, okay. So V dash will be, take the total V naught, it will be split based on these two resistors. So 1 by 1 plus 2. Both of them are in kilo, so the unit doesn't matter. Okay. Now we have V dash. We have V dash, what is I? I is V dash by this resistance 2K. Right? So let's plug this information over here. If we do that, this becomes, okay, V naught into 1 plus 1 by 2. So if you simplify this, this is nothing but 1 by 3. So this should be 1 by 6 milliamps. Okay. So we have V naught over 6 milliamps for the voltage that's given. If you plug in 2.1 here, we will get 0.35 milliamps. Great. So now we have I, we know how to find T. They are just very related. So we know 1 microamp corresponds to 1 Kelvin. So how much would 0.35 milliamp correspond to? Okay, so this should be 0.35 into, first of all, it's in milli, 1000 times higher than this. So there is a factor of 1000, okay, kelvins. And this is just 350 kelvins. So the temperature that resulted in the potential of 2.1 here is 350. Okay. Again, it's a very simple problem, but it might appear tricky because the way to connect this V naught to this T is through this intermediate variable V dash. At this point, you might wonder if I chose 3 simple examples from transducer amplification circuits. The answer is actually no. Okay. Most of this transducer amplification circuits are very simple. Okay. Turns out all the 3 that I chose that also happen to be simple. I hope having seen this video, you'll be able to solve other transducer amplification circuits. I'll see you with more videos, and good luck with your exams and preparation.